Welcome. This is a brief tutorial on how to change coordinates in Atlas. I've launched the software and I've loaded these two files, groups and the types, which you probably want to load always. And for what I'm talking about here, the important file is called coordinates.at, so let's load that. And let's just start with a quick example. Suppose I set RD to be the simply connected root datum of type C2, and I look at the simple roots. They're not what I want. So I would much prefer if I could use the simple roots that I'm familiar with. Let's put those in a matrix. I'd like the simple roots to be 1, -1, 0, 2. So what I need is the change basis matrix between these two. So let's set SR to be the simple roots of this root datum. And what I need is the matrix A times SR, the inverse of SR. So let's look at the inverse of SR. And we see that there's a problem. It's not invertible over the integers. So this requires a little bit of a workaround. And what I do is I set SR inverse D to be invert of SR. And D is 2. And we see that SR inverse is this integral matrix, and SR inverse times SR, well, it's the inverse up to this factor of 2. So let's set C to be A times SR inverse. And up to this factor of 2, this is the matrix that I want. What I mean by that is if I take C and I multiply it by SR, I should get the matrix A, well, up to this factor of 2. So I should really divide C by 2, and that's and I'll do that. The way to do that is as follows. So here's C. I want to divide each of the columns by 2. So let's redefine C to be for V and C do V over 2. That will divide all of the columns by 2, but when I do that, I'm going to get a rational vector, and I prefer it to be an integral vector. So you do it this way, and there's C now as is exactly the matrix that I want. If I multiply C times the simple roots in the bad coordinates, I get the simple roots in the good coordinates. So for example, if I look at rho of this root datum, well, it's the simply connected root datum, so it's the fundamental weight coordinates, and rho is 1, 1, which isn't what I want, but if I wanted to get rho in the coordinates that I like, I'd multiply it on the left by C. As another example, if I look at the positive roots of this root datum, they're a little bit strange, but to get the ones that I want, I multiply them on the left by C. Now, let me mention here that if I had defined this group to be as follows, defined it to be SP4, then I wouldn't have had to go through all of this. When you define a classical group like this, it picks the nice coordinates. So for this particular group, this wasn't really necessary, but there are certainly other times when it is. So let's look at an example of that. Well, before I do that, this process that I just went through, which was a little bit tricky involving the inverse, of course you don't want to have to go through that all the time, and so there's a script which takes care of that for you. So let's take a look at that. That's the script coordinates.at, and there's a description of it up here at the beginning, and what it says is it's a change of basis matrix between the simple roots of RD, that's what the coordinates that the software uses, and the user can provide a matrix called my_roots. And it says the columns of my_roots are the simple roots in your preferred coordinates, and rational vectors are allowed here, vectors or rational vectors. And it's going to hand you the main way to call the software is to say set C to be this change of basis matrix, and then there's the inverse change of basis matrix, which I call D, and then these are satisfy the following. C times the simple roots gives you my roots, and D goes in the other direction. And if you want to see how these functions are defined, you can look down in the file. The main one is this set change of basis right here. And this does what I just did by hand. It computes this inverse and does this little monkeying around with the denominator in order to give you back the correct matrix. Okay, so let's go back to the software. Whoops. Let's go back to the software, and let's do a different example. Let's say that G is GL3R, and we look at the simple roots. Those are the ones in the usual coordinates. And now notice this group has rank 2. There are 2 simple roots. And, semi-simple rank 2. There are 2 simple roots. And rank, but the rank is 3, which is the number of rows. And again, it's chosen nice coordinates here. On the other hand, if you set G to be SL3R, and you look at the simple roots here, well, they have to be it has to be a 2 by 2 matrix, so it can't be these ones. But you can do that using the change of basis. So let's set A to be the matrix that I want, which is 1, minus 1, 0, 0, 1, minus 1. Those are the simple roots that I prefer. And let's set C to be the change of basis matrix for this group SL3R, and changing into these new coordinates given by the matrix A. So let's see what C is. Now you see that it's actually a rational matrix. There's no getting around that. It's necessarily rational but not integral. But let's see, if you multiply C times the simple roots of G, you get the simple roots in the nice coordinates. Now notice everything's rational here because of the C being rational, and so the resulting vectors here are, well, they're written as rational vectors. Let's see, what type is this thing? It's an array of rational vectors, but they are integral, so there's a little command called make integral, which, if it's possible, it converts this into an actual integral matrix. Okay, so for example, again, if I look at rho of G, it's a little bit funny, but if I convert that to the coordinates that I like, I multiply it on the left to get rho in the usual coordinates. And let's set D to be the inverse change of basis matrix for this group and this matrix A. And let's see what D is. Well, now D is a perfectly good integral matrix, and so when that happens, there's another command where you just you add the word integral at the end, and it'll actually give it to you as a matrix. So this is the matrix going in the other direction. And the fact that these two operations are inverse is reflected in the fact that D times C is the identity. So let's see that. Okay, so for example, if you look at the positive roots of G, here they are. If you want to convert them to the roots in your coordinates, you multiply on the left by D. And, well, if you want to convert back again, you multiply, I said the wrong thing, but I typed the right thing. You multiply on the left by C, and then to go back, you multiply on the left by D again. Okay, let's do another example. Let's set G to be the split group of type G2 and look at the simple roots of G. What on earth are those? Well, let's let A be the simple roots that I like, which is 1, minus 1, 0, and 2, minus 1, minus 1. And let's set C to be the change of basis matrix for G with respect to A. And this is integral, so I could say integral. And there's my matrix. And so let's check if I do C times the simple roots of G, I get the roots in the nice coordinates. If I do C times the positive roots of G, I get totally the wrong thing. Oh, I'm sorry. Minus 2, 1, 1. There you go. That, of course, is not correct. I should have put this. And so now let's let C be the change of basis matrix. And now let's do C times the positive roots of G. There we go. And those are the positive roots of G2 in the usual coordinates. And for good measure, let's look at the inverse change of basis matrix for G with respect to A. And now this is a inherently rational matrix, so I can't convert it to an integral matrix, but this is the matrix that goes the other way. So for example, if I took D times minus 1, minus 1, 2, that's the highest root in the nice coordinates, and if I multiply it by D, I get the highest root in the coordinates that Atlas is using. And let's just see that that's really right. The last root is always the highest root, and indeed it's 0, 1. So this is a very simple and powerful tool which enables you to convert coordinates to something that you find convenient. Well, I would be remiss if I didn't do one last example of E8. So that is, let's set G to be the split form of E8. And let's look at the simple roots of G. Well, this is the Cartan matrix. This is a rather strange way to write the roots of E8, but it's a perfectly good way to do it. But of course, it's not the usual one. What I want to use is the usual Bourbaki coordinates, and I've put those in a file. I'm going to load it now, called E8. And I called it this matrix M. It's a rational matrix, so let's look at it this way. So here are the simple roots of E8 in the usual coordinates. The first one is the one with some 1s and minus 1s all over 2, and then a bunch of vectors of the form 1, minus 1, or 1, 1. So that's the coordinates that I like. So let's set C is the change of basis matrix for G with respect to M, and let's see what it looks like. This is a rational matrix. Let's look at it. There we have it. Well, okay, so let's look. What is rho of G? Well, it's fundamental weight coordinates, so it's all ones. But if you want to get it in the usual coordinates, you multiply it on the left by c, and we see the familiar row in these coordinates. And if that's not familiar to you, I suggest you look it up in Bourbaki. One last thing, let's look at the simple roots, the positive roots of g. I'm going to print them like this. So here are the positive roots of E8. It starts off with the simple roots, and then all these others, and then the highest root is all the way down here is 1, the last coordinate. But of course, if you want to see it in the nice coordinates, you multiply each of those vectors on the left by c. And this is the usual highest roots of E8. You see a bunch of these things with 1s and minus 1s over 2. And here at the very end is the highest root with 1, 1 at the end. Okay, I think that's a good place to stop.